Now that I'm filming, I can show that I care. Any questions? My main question is, does anyone use this board besides me? Yeah, I'm seeing marks on here that look similar to what I left on Monday. I just wondering if anyone actually uses this room.
They used to, I'm not sure now.
All right. In the absence of other questions, let's take a look at this problem right here. I have a thick shelled conducting sphere. So just think some metal sphere with a hollow inside. It has an excess charge of 3 nanocoulombs that somehow I just miraculously just threw onto it. In the middle of this, at the very center, I also have a point charge which is negative 4 nanocoulombs, and that's a minus sign there. So the questions are, what is the charge on the inner surface and outer surface, and what is the electric field at some point in the hollow area, within the middle of the thick shell, and then outside at those specified distances. So let's start out with a point 1 centimeter away. How would you go about even solving that? And I know you're tempted to do it, but let's see if we can do it without using calculus. I see some people still writing down, and some people will give that look of, I don't know. You might want to check your notes for there was the day that I wrote it on the right-hand side of the board, at least that's my memory, of shortcuts. What are some of the shortcuts we know?
Uses Gauss's law of electricity.
Say it again?
Gauss's law of electricity.
Well, we will be using that, not for this part, but we will be using that in a second. Oh, actually, we could do it for this part too.
We know that if it's a conductor, we know that the charge is like evenly distributed.
Not necessarily evenly, but distributed where?
On the outer bit of the conductor. Like
Better wording on the surfaces. Surface or surfaces. The examples we've done before, there's just basically been an outer surface, but now we've got an outer inner surface, so charges will be distributed there. It is possible that when I did the shortcuts, I said outer, and it should just not, the word outer should not be there. The charges will be distributed on the surface or surfaces potentially.
Well, since that's the case, we're really only concerned with the surface or the area of it, right? So we can use the area vector to kind of proceed with that using the.
All right, good. So there's a different shortcut. We can use Gauss's law. There's a different shortcut I was going for.
Oh.
That, actually, let me see what you have written down just to see if I shared this with you, or just assume you would be more. Oh, okay. Okay, take that one. That is a surface. Okay. So let's use Gauss's law at this point right here. So basically I create a Gaussian surface, I create some virtual sphere that is at the 1 centimeter mark. And I know that the electric flux through that surface is going to be equal to the enclosed charge over epsilon sub naught. That's the electric field times the area is equal to the enclosed charge over this constant. And what can you tell me about the area vector? Well, in this case, it's a sphere.
Would
But
it be-
generally, in general, can you tell me about an area vector?
It's gonna be the perpendicular to the surface.
Okay, and in the case of a closed surface?
Outward.
Yes.
So it's actually facing outward.
Yep, all right. So we have, in the sphere, we have these area vectors that are pointing outwards. What's the direction of the electric field at the surface of my Gaussian surface?
Same direction?
It's infinitely pointing out.
We'll go with that for right now. Technically, it's a negative charge there in the middle, so the electric field's going in. But the dot product, there's a negative that shows up. We can think through that. We'll deal with that later. All right, so since the electric field and the area vector in this particular case are anti-parallel, then it's just going to be the negative magnitude of the electric field times the area. In other words, I don't have to worry about sine, cosine, or any of that stuff. I don't have to do anything tricky here. It's just my electric field and my area vector are either together or apart. Cosine of 0 is 1, cosine of 180 degrees is -1. Technically, the cosine of 180 degrees is what we're working with here. Bottom line, it's the simpler case.
Can you explain why you have the negative there again? Is it because the electric field is negative at that point? Or what's the charge then?
Officially, the reason why is that I have a dot product is the magnitude of the electric field times the magnitude of the area vector times the cosine of the angle between them.
Okay.
Because the electric field is pointing inwards in this example and the area vector is pointing out. This is 180 degrees. That's -1.
Okay.
That's where it comes from.
Thank you.
Okay. Is equal to the enclosed charge over epsilon sub naught, which is -4 times 10 to the -9 over epsilon sub naught. So the magnitude of my area vector times, well, what's the area of a sphere? Surface area.
4/3 pi.
You said 4/3 pi?
I was thinking about it.
4/3 pi squared.
Almost. You've combined the surface area and volume.
Yeah, I realized I was starting to do that, so.
Yeah. Volume's the one with the 4/3.
Oh, is it just pi r squared then? No.
That's the area of a circle.
4 pi r squared?
That's the one. Just drop the third. So times 4 pi r squared is equal to this, that's -4 times 10 to the -9 over 8.85 times 10 to the -12. And so the magnitude of my electric field, oh, technically, negative there. The negatives are gonna cancel out, and I'm left with 4e -9 over 4 pi r squared, which is 0.01 squared, then 8.85 times 10 to the -12. And we get something that is just absolutely spectacular and will give your life meaning. And if someone calculates that, we mark down a little bit here.
You said the negatives cancel out like up top, so now it's just 4e9 or 4e. Is that 4e -9?
Yes, that negative still stays.
Epsilon's the constant, right?
Pardon?
Epsilon's a constant, right?
Yes. the value of epsilon is specific to the medium, and we're assuming free space there.
Got it.
I got 2.82 to the negative 17.
2.82 times 10 to the,
Negative 17.
no. It's gonna be to the positive something. Do you remember the parentheses around?
Yeah, I think I might have.
So that would be 12, 13, 14, 16. Seven. Those would cancel out. Third.
Is 4 pi also squared, or is it just 0.01? that's squared?
Just the 0.01. Anna, what you got? You look like you got an answer.
I have 3.5, well, 3.6 times 10 to the positive 2, 3, 4, 5. I don't know if that's correct.
Let's do the fifth. Anyone else?
I kept getting progressively, like, smaller numbers, like, it would be negative, like, it was negative to the, like, negative 17th, and now it's to the negative 25th.
Yeah, no, I definitely gonna be times 10 to the positive number. Daniel, what do you have?
I have 2.82 to the negative 17. 10 to the negative 17, so going back. Let's see.
We can do it the old fashioned way here. We take the non-exponent part. So that, this right here, that's just 10 to the negative 2 squared. So we have 4 over 4 pi times 8.85 on the denominator. That's the non-exponent part, times 10 to the negative 9th over 10 to the negative 4th and 10 to the negative 12th. So that's 10 to the 7th. And then I've got this piece right here, which I'm guessing is either 2.82 or actually it would be point. That cancels out.
27.8.
Say it again.
27.8 is what.
This denominator,
Oh, just the denominator.
or
The-
the which part is 27.8?
4 divided by 4 pi. 8 point, and then parentheses 8.85. I just threw that whole thing into the calculator. But just the denominator, you said?
Yeah. So you just did this piece right here.
Yeah.
Should have gotten a fraction, something under 1.
Yeah, now that I'm looking at it, this makes sense.
So you're looking for pi times 8.85.
And then the reciprocal of that.
I have 2.8.
That's 2.8 times 10 to the,
I just did the reciprocal of pi times 8.85.
yeah, pi times 8.85 is bigger than 1, so when I take the reciprocal, I should get something less than 1.
One would think that. Well, pi times 8.85, I have 27.8.
There's the 27.8. So this is 1 over 27.8. And the reciprocal would be 2.8 times, all right, so that's roughly a third. No, that's roughly 3.03. So this would be 0.028.
Oh, yeah. When I add extra parentheses, I've got 0.036.
Pi times 8.5 is 27.8.
Okay. And then the reciprocal of that, 0.036.
My calculator says that pi times 8.5 is 26.7, and that's,
All right.
So we don't know what the answer is.
so I can trust Anna's calculator more than my calculator.
All right, so. I got 27.8, and then 3.6 times 10 to the negative 2, times 10 to the 7th. So, what Anna said originally, which no one else wanted to confirm, that. If you're not getting that, unless there's another careless error somewhere, so we had 4e9 negative, 4.
How I get tasted of the pints into consideration when you're dividing it or whatever? I think you're right.
So I get more, my denominator in the original problem, 1.11 times 10 to the negative 14th. Then I do the division, and then I get just under 360,000. All right. This is the magnitude of the electric field. Well, let's throw a unit. What are the units while we're here?
Is it Newton meters per coulomb?
Squared per coulomb.
Too much. What'd you say?
Newton meters squared per coulomb
No, even more too much.
of the electric field.
Electric field.
Newtons per coulomb.
Newtons per coulomb. A Newton meter per coulomb would be a volt, actually. Newton meter squared per coulomb would, oh, that would be electric flux.
That's what.
All right, so that is the magnitude. Of course, we got a positive answer because I would expect a positive answer for a magnitude. That's the result of putting in the minus sign here, is that we actually got a magnitude. But let's think through the direction. I know that the electric field is going to be pointing towards the negative charge, and so I have to think through that piece, and so I get negative 3.6 times 10 to the 5th newtons per coulomb. An important takeaway here, the piece that I was hoping that you were going to say earlier, but I didn't see it in Daniel's list of shortcuts. When I have a ring of if I have a spherically symmetric distribution of charge, any charges that are outside the point in question, in other words, any charge that is outside this distance from the center, where I'm doing my Gaussian surface, has no impact on the electric field. This goes in league with the electric field inside a conductor is 0. So, therefore, I can ignore any of the electric charge coming from here. I only care about what's on the inside. So it's reflected in Gauss's law.
Can I ask a quick question about
Yes.
that? I feel like conceptually that would make sense if it was pointing outwards, but since the electric field is pointing inwards towards the negative charge, it seems like charges that are external to that would influence the electric field, and I don't understand why they don't.
It's the same type of argument of the electric field is pointing inwards because I have a charge right there in the middle. And that matters. It's the charge is out here. because you're gonna get still, because of spherical symmetry, you're gonna get a spherically symmetric ring of charge here and there, or, you know, however it's gonna be spherically symmetric. So, we're left with this, I got a bunch of charges around the outside here, I'm looking at this point. I'll make all these negative. So I have these electric field lines going from this point to pointing towards the negative charges at that point. I've got these charges right here, which are a lot closer, so they would have a stronger electric field at this point. But I got more charges over there with weaker electric fields, and they all end up canceling out. So ultimately, the electric field is going to be 0 inside because of, well, as I just said, because of canceling out. I got more of less here, less of more here, and it works out just right. You're not appear convinced by my hand-waving argument.
I fully understand this concept. I feel like it didn't answer my question, but I'm okay with that. It's okay. I'll think about it.
Okay.
We'll
Sorry.
probably cover it. It's all good.
All right. The electric field at 4 centimeters. Now this one, I saw in Daniel's notes, as well as, I just said it like 2 minutes ago.
Oh, yeah, same process?
No, we need to do the shortcut first before we can do the process.
Just don't fully understand the shortcut.
So what are the shortcuts? You had them there. Anyone else can read them out too, what you had before.
You're not talking about the electrostatic equilibrium?
Yeah, we're talking about electrostatic equilibrium.
Is it 0 because it's conductive?
Yes. The electric field inside a conductor in electrostatic equilibrium is 0.